Acids and bases 3. The pH scale. Essential ideas. The pH scale is an artificial scale used to distinguish between acid, neutral and basic or alkaline solutions. Nature of science. Occam's razor. The pH scale is an attempt to scale the relative acidity of a wide range of hydrogen concentrations into a very simple number. The methods we use to measure pH. We can use pH sensors, like electronic sensors, good old-fashioned pH indicator paper, and universal indicator, which you would add to a solution that changes colour. You can see here on the universal indicator, red is a strong acid, yellow weak acid, green is neutral, weak base is bluish, and a strong base is a violet. So what do the values mean? You can see that Coca-Cola is 2.7, tomato sauce 3.8, your face 5.5, milk 7, blood 8, bleach 13. What do these numbers mean? Well, the pH is a measurement of the acidity of a solution, and more specifically, pH is a measurement of the concentration of hydrogen ions or hydronium ions in a solution. The term pH comes from the phrase power of hydrogen or potential of hydrogen. If you look at this scale here, you can see on the left, if you've got 1 mole decimeter cubed here, the hydronium ion or hydrogen ion, you'd write the exponential notation like this, and the pH would be 0. Notice the 0 there and the 0 there. Let's look at another one. Here, you've got 0.1 moles per decimeter cubed concentration of H plus or H3O plus. So exponential notation would be 1 times 10 to the minus 1, and so the pH would be 1. Down here, minus 7, so pH of 7. What about minus 12? pH of 12. So it's very straightforward, and you can see that the lower the concentration of ions, of protons or hydronium ions, the smaller the exponential notation, and you end up with a very, very simple series of numbers to represent quite a large difference in concentration. Obviously the acids have a smaller number, bases have a larger number. Stuff in the middle, about 7 is weak. 0 would be very strong. 8 would be weak. And say up to 14, super strong base. The pH scale is a logarithmic scale. A 1 unit change in pH is a 10-fold change in the concentration of hydrogen ions. The logarithmic scales are useful in representing very large or very small numbers as simpler numbers. As pH increases, a solution becomes less acidic or more basic. And as the pH decreases, a solution becomes more acidic or less basic. When the pH of a solution changes from 3 to 2, when it lowers from 3 to 2, the solution becomes 10 times more acidic. When the pH solution changes from 3 to 6, the solution is 1,000 times less acidic. Given these solutions here, A, B and C, with pHs of 6, 2 and 3, all of them are obviously acidic because they're below 7. The most acidic is B, it has the lowest number. The least acidic would be A, it has the highest number. B is 10 times more acidic than C because there is a difference of 1. Okay, and you're just multiplying. The difference, say 1, you'd add 1 0. That's how I like to think of it. Here, you've got A is 10,000 times less acidic than solution B. And you've got 2. The difference between 6 and 2 is 4, and we have 4 zeros. Calculating pH and the concentration of protons. pH is a negative log 10 to the concentration of H+. You'd have to use, there'll be two types of questions you might face. Some you'd need a calculator, some you wouldn't. Question 1 here, you can see calculate the pH of a solution with a concentration of protons of 1 times 10 to the minus 9 moles per decimeter cubed. You can see in both cases it says 1 times 10, 1 times 10, so you wouldn't need a calculator here. It's crazy straightforward. The pH is a negative log 10. You'd put in your number here, and whatever the power is, the minus log 10, when you minus log 10 it just becomes the number itself. Okay, and minus of minus is obviously a positive, so it would be 9. Exactly the same thing would be true here. You have power of minus 3 moles per decimeter cubed, so the pH would be 3. It's a bit more difficult if you don't have 1 here, and you would have to plug it into a calculator, but it's still straightforward. You just put the 7.5 times 10 to the minus 9 minus log 10 it, and the calculator will kick out your answer. Oh no, 1 minute. There we go. Here's another no calculator example, type of question you might get. Calculate the concentration of protons of a solution with pH 5. Well, we know that you're just gonna, it would be 10 to the minus 5 if that's the concentration. So 1 times 10 to the minus 5 moles per decimeter cubed. If you've got a fraction or a decimal, it's a bit more tricky and you would be allowed to use a calculator. But again, it's fairly straightforward. 10 to the power of minus 11.3, plug it into your calculator and it will give you the answer. The water equilibrium. Water is able to dissociate to a very small extent, even though it is a covalent molecule. So we're getting some dissociation. There's two ways of thinking of it. One is water's going to the hydrogen ion and hydroxide ion. Another way is thinking the hydronium ion and the hydroxide ion. But only 1 or 2 molecules per billion water molecules dissociate. That's why water is a non-electrolyte. It's not going to conduct electricity because it is primarily existing, pen isn't working, it's primarily existing as molecules, as a non-charged particle. And obviously you have to have charged particles for to act as electrolyte or to be able to conduct. And so because the equilibrium is so very far this side to the left, you've got hardly any of these charged particles existing in solution. But it is an equilibrium, and that means it can be described by an equilibrium constant, and as capital K little w is the dissociation constant for water. And we'd have, we can write it like this, the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. At 25 degrees, it's about 1 times 10 to the minus 14. So it's extremely small. This magnitude of K value suggests, what does it suggest about the position of the equilibrium? Well, since K is much smaller than 1, the position of the equilibrium lies very much to the left, to the reactance side. Water primarily exists as a molecule, as I've just said. The concentration of H plus and OH minus ions is very low. But both H plus and OH minus are still present in water and in any aqueous solution. There's just not very much of it about. Can you press pause, go into this PhET simulation, and then record a series of measurements and think about how the dilution affects the pH of the substance. You've got 3 different substances. It's a bit gross, but do it anyway. Then you can fill in this table from that. Okay. The water equilibrium and aqueous solutions. All aqueous solutions have both H plus and OH minus ions present. And there's the equilibrium there. The relative concentrations of the ions, of the hydrogen ions and the hydroxide ion, determine if the solution is acidic, basic or neutral. Neutral solutions, the hydrogen ions, the concentration of hydrogen ions equals the concentration of hydroxide ions. In acidic solutions, the concentration of of the hydrogen ions is greater than the concentration of hydroxide ions. Conversely, in basic solutions, the concentration of hydroxide ions is greater than the hydrogen ions. In neutral solutions, the concentration of hydrogen ions is 10 to the minus 7 moles per decimeter cubed. In acidic solutions, the concentration is greater than 10 to the minus 7 moles per decimeter cubed. In basic solutions, it is less than 10 to the minus 7. For the hydroxide ions, in neutral solutions, it is 10 to the minus 7. In acidic solutions, the concentration of hydroxide ions is less than 10 to the minus 7. And in basic solutions, it's greater than 10 to the minus 7 moles per decimeter cubed. All aqueous solutions have both H plus and OH minus present. Now let's look at this table. Note one thing about it. As H plus decreases, let's see, as this H plus will follow 1 through to 14, you can see it's quite large here, 10 to the minus 1, getting smaller and smaller and smaller and smaller and smaller till you get to 10 to the minus 14. OH minus is increasing conversely, so it's starting at 13 and getting smaller and smaller and smaller and smaller and smaller. Oh, sorry, it's getting bigger and bigger and bigger and bigger and bigger as this gets smaller and smaller and smaller. So the concentration of hydrogen ions decreases as the hydroxide ion increases. Also, another interesting thing to note, at any pH value, the product of the concentration of the hydrogen ions and the concentration of the hydroxide ions is 1 times 10 to the minus 14. And you can see there, minus 1, minus 13 comes to minus 14. Pick another one, minus 8 and minus 6 together. The product of these would be 10 to the minus 14. Okay, some examples. Can you press pause and see if you can answer these questions? Okay, which are false and which are true? A solution of ethanoic acid has a pH less than 7. Well, it's an acid and all acids have pH less than 7, so that is true. B. The concentration of hydrogen ions is less than the concentration of hydroxide ions. Well, we know that hydrogen ions are responsible for acidity, and the higher the concentration of hydrogen ions, the more acidic it is. And since we're talking about an acid, this will be false. We expect the hydrogen ions to have a higher concentration than the hydroxide ions. There are only hydrogen ions present. This most certainly is incorrect. There's both hydrogen ions and hydroxide ions in the solution. But there will just be a greater concentration of hydrogen ions than hydroxide ions. Let's have a look at this one. They're saying that the concentration of hydrogen ions will be less than 1 times 10 to the minus 7. And this is true. This is false. This is neutral. And we want to have, and the hydrogen ions will be at a greater concentration than this if it were to be acidic. We're talking about an acid, so this should be the other way around. When ethanoic acid is diluted, its pH increases. This is of course true. If you think about it, you've got a certain amount of hydrogen ions in the liquid or in solution. If you're adding loads more water, you're diluting it. You're diluting the concentration of the hydrogen ions, and therefore it is moving towards neutral. So its pH will increase towards 7. Okay, press pause again, see if you can answer these ones, and then we'll go through them. So it says we've got a solution with a concentration of hydrogen ions of 1 times 10 to the minus 9. So we know that it's basic. It's got a pH of 9. This solution is a base, yes, because it's it has a pH of 9, and so it's greater than 7. The hydroxide ions concentration will be greater than 1 times 10 to the minus 7. Remember, 1 times 10 to the minus 7 is neutral. That's a pH of 7. And we do know that the hydroxide ion concentration must be greater than this because it's basic. See, there are only H plus ions present in the solution. No, it's incorrect. There will be OH minus solution 2. It's an aqueous solution. and the pH of this solution is below 7. Well, a pH below 7 is acidic. We know that this is in fact basic, so that is incorrect. Calculating the concentration of hydrogen and hydroxide ions in solution. Every aqueous solution has both hydrogen and hydroxide ions. The water equilibrium can be used to find the concentration of hydrogen ions and hydroxide ions and pH in any solution. We've got this dissociation constant for water here. For the hydrogen ions and hydroxide ions, it's 1 times 10 to the minus 14. So, if you wanted to calculate a hydroxide ion, and you were given the concentration of hydroxide ions, If you want to calculate the concentration of a hydrogen ion, and you were given the concentration of hydroxide ion, you would just plug in the concentration of the hydroxide ion, because you know what Kw is, and 1 times the other would give you the concentration of the hydrogen ions. Or if you want to calculate the pH, once you've calculated that H+, you can just plug it into here and calculate the pH. Okay? Although this is HL only, we'll have a quick look. If you want to calculate the concentration of hydroxide ions, and you were given the concentration of hydrogen ions, you could use this known number, 1 times 10 to the minus 14, divided by the given concentration of hydrogen ions, and you'd have the concentration of hydroxide ions. Then if you want to work out the pOH, you could just use this equation here. Right, calculate the concentration of hydroxide and the pH of a solution where the concentration of hydrogen ions is 5 times 10 to the minus 5. First of all, we'll use this equation to find OH. We know the Kw is 1 times 10 to the minus 14, so we just plug in the concentration of hydrogen ions, because it's given in the question. We get the concentration of the hydroxide ions. Then we know the pH minus log concentration of hydrogen ions will give us the pH. We'll get given that in the question. Plug it in to get the answer. Example 2, calculate the concentration of hydrogen ions and the pH of a solution where the concentration of hydroxide ions is 2 times 10 to the minus 3. First of all, we can use this equation. We know Kw is 1 times 10 to the minus 14. We're given the concentration of hydroxide ions. That divided by the other one gives us the concentration of hydrogen ions. Then use the log, minus log 10 of the concentration of hydrogen ions, which we've just calculated, plug it in, and it gives you your answer. You might get no calculator examples of this, so let's have a look at one of those. The solution has a pH of 3, calculate the concentration of the hydrogen and hydroxide ions. Where we know H plus is 10 to the minus pH, we know the pH is 3, so 10 to the minus 3 is 1 times 10 to the minus 3 moles per decimeter cubed. It's straightforward. Then we can use our equation, which minus will be Kw, 1 times 10 to the minus 14, divided by the concentration of the hydrogen ions, gives us the concentration of hydroxide ions. And that's the end of this presentation. Splendid.